To determine the required size of a copper equipment grounding conductor, or EG, for a 200 amp 480 volt branch circuit fed with 3/0 THW conductors, you must refer to the National Electrical Code, specifically section 250.122. This section dictates the minimum size of equipment grounding conductors based on the rating or setting of the overcurrent protective device in the circuit. In this case, the overcurrent protective device is rated at 200 amps. To find the appropriate conductor size, you will need to consult table 250.122 in the NEC. This table correlates the size of the overcurrent protection device to the minimum size of the equipment grounding conductor. Looking at table 250.122, find the route that corresponds to a 200 amp overcurrent protective device. The table will specify the minimum size copper equipment grounding conductor required. For a 200 amp overcurrent device, the minimum size copper equipment grounding conductor required is number 8 American wire gauge, or AUG. Therefore, for a 200 amp 480 volt branch circuit fed with 3/0 THW conductors, a number 8 AWG copper equipment grounding conductor is the minimum size required. It's crucial to always consult the most recent edition of the National Electrical Code for the most up-to-date requirements and ensure compliance with all applicable regulations. There are several factors to consider when selecting and installing equipment grounding conductors. Firstly, material which grounding conductors can be made of copper, aluminum, or copper-clad aluminum. Copper is the most common choice due to its excellent conductivity and corrosion resistance. Secondly, size, which the size of the grounding conductor is determined by the rating of the overcurrent protective device in the circuit, as per NEC table 250.122. Thirdly, type, which grounding conductors can be bare or insulated. Insulated grounding conductors must have a green or green with yellow stripe outer finish. Fourthly, installation, which grounding conductors must be installed in the same raceway or cable as the circuit conductors. It must be securely connected to all metal enclosures, equipment, and devices. Fifthly, continuity, which the grounding path must be continuous and permanent. Connections must be made using approved methods, such as listed connectors or exothermic welding. Sixthly, identification, which grounding conductors must be clearly identified. Insulated grounding conductors must be green or green with a yellow stripe. Bare grounding conductors can be identified by tags or markings. Seventhly, protection, which grounding conductors must be protected from physical damage. They should be installed in a way that minimizes the risk of being cut, abraded, or otherwise damaged. Eighthly, accessibility, which grounding conductors should be accessible for inspection and testing. Connections should be located in accessible locations. Ninthly, bonding, which all metal enclosures and equipment must be bonded together to create a low impedance ground path. This helps to minimize the risk of electric shock. Tenthly, grounding electrode system, which the equipment grounding conductor must be connected to the grounding electrode system. This provides a path for fault current to return to the source. Understanding the purpose of equipment grounding conductors is also important. Firstly, protection against electric shock, which equipment grounding conductors provide a low impedance path for fault current to flow back to the source, causing the overcurrent protective device to trip and to energize the circuit, thus minimizing the risk of electric shock. Secondly, fault current path, which equipment grounding conductors provide a dedicated path for fault current to flow back to the source. This helps to ensure that the overcurrent protective device will trip quickly and reliably. Thirdly, voltage stabilization, which equipment grounding conductors help to stabilize the voltage on electrical equipment. This can help to reduce the risk of equipment damage and improve the overall performance of the electrical system. Fourthly, electromagnetic interference reduction, which equipment grounding conductors can help to reduce electromagnetic interference, or EMI. EMI can cause problems with electronic equipment, such as computers and communication devices. Fifthly, lightning protection, which equipment grounding conductors can provide a path for lightning current to flow to ground. This can help to protect electrical equipment from damage caused by lightning strikes. Sixthly, safety, which equipment grounding conductors are an essential safety feature of electrical systems. They help to protect people from electric shock and equipment from damage. Seventhly, code compliance, which the NEC requires that all electrical equipment be properly grounded. This helps to ensure that electrical systems are safe and reliable. Eighthly, equipment protection, which by providing a low impedance path for fault current, the equipment grounding conductor protects electrical equipment from damage during a fault condition. Ninthly, system integrity, which proper grounding helps to maintain the integrity of the electrical system by ensuring that all components are at the same potential. Tenthly, reliability, which a properly grounded electrical system is more reliable because it is less susceptible to voltage fluctuations and other electrical disturbances. When working with electrical systems, it is essential to have a strong understanding of grounding principles and the requirements of the NEC. Always consult with a qualified electrician or electrical engineer if you have any questions or concerns. Proper grounding is critical for the safety of personnel and the reliable operation of electrical equipment. Remember that electrical work can be dangerous, and it is always best to err on the side of caution. If you are not comfortable working with electricity, hire a qualified electrician to do the work for you. Safety should always be the top priority when working with electrical systems. It's also important to remember that local codes may vary from the NEC. Always check with your local building department to ensure that you are following the correct requirements. In addition to the NEC, there may be other applicable standards, such as those published by the Institute of Electrical and Electronics Engineers, (IE), or the National Fire Protection Association, or NFPA. Stay informed about the latest developments in electrical safety and technology. Attend training courses and workshops to keep your skills and knowledge up to date. By following these guidelines, you can help to ensure that electrical systems are safe, reliable, and code compliant. This information is for educational purposes only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or electrical engineer before performing any electrical work. The information provided is based on the NEC and general electrical practices. Always refer to the latest edition of the NEC and local codes for specific requirements in your area. Working with electricity can be dangerous. Always take appropriate safety precautions, such as wearing personal protective equipment, or PPE, and de-energizing circuits before working on them. If you are not comfortable working with electricity, hire a qualified electrician to do the work for you. It is also worth noting the importance of proper termination and connection methods for grounding conductors. Firstly, use listed connectors, which always use connectors that are listed for the specific application. These connectors have been tested and certified to meet safety standards. Secondly, tighten connections properly, which ensure that all connections are properly tightened to the manufacturer's specifications. Loose connections can cause resistance, which can lead to heat buildup and potential failure. Thirdly, avoid dissimilar metals, which avoid using dissimilar metals in connections, as this can lead to corrosion. For example, do not use aluminum connectors with copper conductors. Fourthly, protect connections from corrosion, which protect connections from corrosion by using appropriate sealants or coatings. This is especially important in damp or corrosive environments. Fifthly, inspect connections regularly, which inspect connections regularly for signs of corrosion, damage, or looseness. Repair or replace any damaged or corroded connections immediately. Sixthly, use proper tools, which use the proper tools for making connections. This will help to ensure that connections are made correctly and safely. Seventhly, follow manufacturer's instructions, which always follow the manufacturer's instructions when making connections. This will help to ensure that connections are made correctly and safely. Eighthly, document connections, which document all connections, including the type of connector used, the torque applied, and the date of installation. This will help with troubleshooting and maintenance in the future. Ninthly, consider exothermic welding, which for critical applications, consider using exothermic welding to make connections. Exothermic welding creates a permanent, low-resistance connection that is highly resistant to corrosion. Tenthly, provide strain relief, which provides strain relief for grounding conductors to prevent them from being pulled or damaged. This is especially important in areas where there is a lot of vibration or movement. By following these guidelines, you can help to ensure that grounding connections are made correctly and safely. This is essential for the safety of personnel and the reliable operation of electrical equipment. Remember that grounding is a critical aspect of electrical safety. Always take the time to do it right. In addition to the above, it is important to understand the concept of impedance in grounding systems. Impedance is the total opposition to current flow in an alternating current or AC circuit. It is made up of resistance and reactance. In grounding systems, low impedance is crucial for ensuring that fault current can flow quickly and reliably back to the source. High impedance in the grounding path can limit fault current, which can prevent the overcurrent protective device from tripping quickly. This can increase the risk of electric shock and equipment damage. Several factors can contribute to high impedance in grounding systems. Firstly, loose connections can create resistance, which increases impedance. Secondly, corrosion can also create resistance, which increases impedance. Thirdly, long conductor lengths can increase impedance due to the inductive reactance of the conductor. Fourthly, small conductor sizes have higher resistance, which increases impedance. Fifthly, improper bonding can create high impedance paths for fault current. To minimize impedance in grounding systems, follow these guidelines. Firstly, use short conductor lengths which keep grounding conductor lengths as short as possible. Secondly, use large conductor sizes which use grounding conductors that are large enough to carry the expected fault current. Thirdly, make tight connections which ensure that all connections are tight and secure. Fourthly, protect connections from corrosion by using appropriate sealants or coatings. Fifthly, bond all metal parts together to create a low impedance ground path. Sixthly, use a dedicated grounding conductor for each circuit. Seventhly, avoid ground loops which can create circulating currents and increase impedance. Eighthly, test the grounding system regularly to ensure that it is functioning properly. Ninthly, follow the NEC requirements for grounding and bonding. Tenthly, consult with an expert consult with a qualified electrician or electrical engineer if you have any questions or concerns about grounding impedance. By minimizing impedance in grounding systems, you can help to ensure that they will function effectively in the event of a fault. This is essential for the safety of personnel and the reliable operation of electrical equipment. In summary, determining the correct size of the equipment grounding conductor involves understanding the NEC requirements, specifically Table 250.122, and applying them to the specific characteristics of the electrical circuit, such as the overcurrent protection rating. The minimum required size for a 200 amp circuit is number 8 AWG copper. Always consult the latest edition of the NEC and local codes for the most accurate and up-to-date information.